Okay. All right. Well, good morning to you all, and I hope you guys are doing well. Um, we'll start with today's lecture. All right. So today we are going to cover the topic of gradient descent. This is going to be a method for optimization that we will make use of. So I just kind of want to cover the basics of how this works. Okay. And so prior to all of this, we were doing a bunch of OLS regression stuff. Okay, we were looking at minimizing the loss function, and so our loss function has been the mean squared error. You know, we take the difference between the actual value t sub n and the predicted value, which is going to be f of x sub n. Okay, so for some given given value x sub n, we have a prediction, and this is has been our loss function, right? And I kind of skimmed over it, but we did partial derivatives to kind of optimize that. We did derivatives in vector notation, and it wasn't too bad. And what we did is, after we took the derivative, we set it equal to 0 and solved for that vector, or for the derivatives. Okay. Sometimes this loss function can become very complicated. And it's also possible that, you might be able to find the derivative, okay? You might be able to find the derivative, but figuring out where the derivative is equal to 0, that could end up being a challenge, okay? So calculating for where the derivative equals 0 could become very difficult, or maybe even impossible. And so in those cases, how do we solve, or how do we find a local minimum? Okay, well, we have a computational method, and the one we're going to cover today is gradient descent. All right, and so our goal is to find kind of the parameter estimates that are going to minimize the loss function for our observed data, right? So we did this earlier, but we treat the data as fixed values. And the loss function itself, the loss is a multidimensional function of the parameters that we need to estimate. So if we need to estimate the slope and the intercept, then we have a two-dimensional loss function. Okay, we have a function that depends, whose values depend on the slope and the intercept. And if you took 102A with me, we covered coordinate descent, and we looked at optimizing one variable at a time. And what we're going to look at today is going to be gradient descent, where we're going to look at kind of both variables at the same time to optimize. Okay. And so the idea behind gradient descent, well, we first have to understand the gradient, and which is kind of a multi-dimensional analog to the derivative. Okay. So if you have a function of just one variable, then the derivative represents the slope of the tangent line, okay? And if you have a function of several variables, then the gradient is the direction of the greatest increase of the function at some point x, okay? So the gradient is going to represent kind of the direction of steepest ascent, okay? It's going to indicate in which direction you should travel if you want to increase or change the value of the function the greatest, okay? And the magnitude of the gradient is going to be the rate of increase in that direction. And so here's kind of the idea behind gradient descent, is that if you're at some location, you can use the gradient to find the direction of the greatest increase, right? So you imagine a two-dimensional function where you now have a surface, okay? You have a surface over 2 dimensions, right? The function, the input space is, you've got it x1 and an x2, okay? and then the value of the function creates some kind of surface. And so if you've got a surface like this, you might be at some location, and the gradient is going to point in the direction of steepest descent. Okay, and so what we're going to do is you are going to move, if the gradient points in this way, you are going to move in the exact opposite direction. You're going to move in the opposite direction, and that should point downhill, right? And so you take a step downhill, and then you repeat the process. You find the gradient, which will point upwards, and you say, well, I'm going to go opposite of up, and you'll take a step downhill. And if you continue this, then you should reach at least the bottom of the hill, or at least the bottom of some kind of valley, a local minimum of some kind. Okay? And so what this looks like mathematically is actually quite simple. Okay, this is the entire gradient descent algorithm. This one line, it's one line. The gradient descent algorithm is one line. It's that you have some multidimensional function f. Okay, it's a f of some vector w. So the input is a vector, multidimensional vector, and f, the function of this, returns a single scalar. Okay, and so if you are currently at some point, let's say w at time n, then the next value, w at time n plus 1, okay, is going to be w at time n minus, okay, and it's the gradient of f at wn, okay, multiplied by some kind of scaling factor. So all you're doing is you're going to take your current location. So if you're currently at wn, then the next value, wn at plus 1, is going to be wn, your current location, minus some direction here, okay? So the gradient here is going to be a vector pointing in some direction, all right? And you're just going to take a small step, all right? And we multiply it by gamma. Gamma, sometimes we also call it lambda. Gamma is some kind of scaling factor, okay? It's what we call our learning rate, or some kind of constant, okay? And the only restriction is that it has to be positive, okay? But it can be less than 1, it can be greater than 1. It just has to be some kind of positive scaling factor. And then this is called nabla f. Nabla f, this upside down triangle, is the gradient of f at location w, okay? W sub n. So wherever you are at w time n, this is the gradient of f at that location. So let me just show you what this might look like for a simple function here, okay? So here I've got some kind of two-dimensional function, x1 squared minus 2x1. Okay, oh, sorry, a couple questions. Okay, one, is this similar to Newton's method? A little bit different, okay? Newton's method is for root finding, and even if you apply it for the derivative, it's still a root finding method. And what you're doing is you take the derivative of something and you follow the derivative all the way down until it crosses the x-axis, and that's where you would pause. With gradient descent, it's like you take the derivative and you just move some increment in that direction of the derivative. Okay, so it's not. It's a little bit different. It's similar only in the aspect that a derivative is involved, but the kind of the principle is a little bit different. Okay, Gavin asks, for the algorithm, what is the stopping criterion? Yeah, this is a tricky thing. The stopping criterion is keep going until you don't make a difference, like the next iteration doesn't change. Okay, and or that the change is so small that you feel like you can stop. Okay, so the stopping criterion. So one thing is that as you get closer to, yeah, you set an epsilon and you keep going, right? As you get closer to the minimum, your gradients will get smaller, more and more shallow, more and more small, and so you just keep taking smaller and smaller steps. So it's kind of like reducing the remaining distance in half. You never actually reach the actual end there. But okay, so let me just do an example here. So here's our function. It's a function of x1 and x2. And so I've got x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. All right. And so, so here I'm going to do it representing the gradient as the vector of the partial with respect to x1 and the partial derivative with respect to x2. So I'm going to start it off that way, but then, but we can also do this in vector notation as well. So anyway, we are going to take the partial derivative of this function with respect to x1. Okay, so x1 squared becomes 2x1, minus 2x1 becomes minus 2, and minus 0.5 x1 x2 becomes, with respect to x1, becomes minus 0.5 x2, right? And then x1 is not involved here. It's a constant with respect to x1, so so that zeroes out. Okay, and then there's a comma here to indicate this is the second, the partial derivative with respect to x2. And so this doesn't vary with respect to x2. This term 2x1 does not vary with respect to x2. This varies 0.5 x1 with respect to x2, and then 2.5 x2 squared becomes 5 x2. Okay. All right. So that's the gradient with respect. That's the gradient of f. Okay. And right now it's represented as the partial derivative with respect to x1 and the partial derivative with respect to x2. Okay, so here is what the contour plot might look like for this two-dimensional function. Okay, and this is what the plot would look like in 3 dimensions. You know, we've got this kind of what do I call this? Paraboloid surface. Okay, some kind of parabolic surface here. So this is what it looks like top down, and then this is kind of what the surface looks like in 3D. And so let me just show you how gradient descent would work. Okay, so let's say I start off at some arbitrary location, -5, 4. Okay, so -5, 4 would be right here. Wait, what did I say? -5, +4. Okay, so -5 is over here, +4 is up here. Okay, so we're starting right around this corner up here. Okay, we're starting close to this corner up here. And what I'm going to do is at this location, I would calculate the gradient. Okay, and the gradient, so I guess I would be kind of in this corner, and we're saying, like, which direction would I need to travel in order to climb the surface as fast as possible? And I would probably have to climb in this direction, or you know, in some direction like this. Okay, starting here, and I would go this way if I wanted to go higher up. Okay, so so the gradient at that location, okay, is just a matter of plugging in -5, 4 into the gradient that we found earlier. So when we found the gradient earlier, we did the partial derivatives, and for with respect to x1, it's going to be this. I plug in -5, so I got 2x1, so 2 times -5 minus 2 minus 0.5 times 4, and when I do that, I get -14 for the partial derivative with respect to x1. And then as far as the partial derivative with respect to x2, it's this, -0.5 x1 plus 5 x2. I plug in these values, and I get, this becomes positive 2.5, and this becomes 20. And so the gradient is going to be -14, 22.5. Okay, so the gradient with respect, the gradient of the function of this two-dimensional function is itself 2 dimensions. It gives us a direction, okay, and saying that I should go -14 in the -14 and up 22.5. Okay, as far as this goes, if we're located here, the direction of travel would be -14, 22.5. And so here I'm going to use a step size of 0.1, okay, and this is just arbitrarily chosen right now, okay. And what we're going to do is that the at the next iteration, okay, so I'm currently at time 0, and so my next iteration, the value, my coordinate at time 1 is going to be my coordinates at time 0 minus gamma times the gradient, okay? So my coordinates at time 0 is -5, 4, that's where I currently am, and I'm going to subtract off gamma 0.1 times the gradient, which we just calculated, to be -1422.5, okay? So I'm at -5, 4, and I'm going to subtract off 0.1 times the value of the gradient that we just calculated, -14, 22.5. Okay, so multiplying this, I get, we're going to basically add 1.4 and subtract off 2.25. And so our next coordinate is going to be -3.6. -5 plus 1.4 is -3.6. And 4 minus 2.25 is 1.75. And so at if I start off at -5, 4, my next iteration will take me to -3.6, 1.75. And so let me just kind of show you what this looks like on the plot. Oops. Okay, so I start off at -5, 4, and I end up at -3.6, 1.75. Okay, so all I've done is I've taken a step kind of down the hill. Is that okay? Give me a green check if you're good so far. And let me give you the answer, first quiz answer. First quiz answer for today, it's Wednesday, is the letter B, B as in boy. Okay, first quiz answer, the answer is B as in boy. Okay, so I got some yeses from, I guess, about 36 people. The rest of you, I hope you guys are doing okay. Okay, let me go back a couple slides. So this is what we did in using partial derivatives. Okay, and here is just to kind of code this up. Okay, here I'm still doing partial derivatives here. So if I code this up, this is the function x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. And the gradient, this is using partial derivatives. I said, okay, the gradient partial with respect to f1, so df dx1 is going to be 2x1 minus 2 minus 0.5 x2. And then partial df with respect to, oh, this should be an x2. Partial with respect to x2 is negative 0.5 x1 plus 5 x2. And I just kind of combine those answers together, and I return this vector df dx1 and df dx2. And if I plug in the values that I have, okay, which I said I'm going to start off at -5, 4. When we calculated by hand, we've got the gradient is -14, 22.5, and indeed that's what we get, -5, 4. We get the gradient to be -14, 22.5, and then the next iteration. So if I start here, I'm going to subtract off gamma times the gradient, and it says indeed -3.6, 1.75, which is what we calculated here, -3.6, 1.75. And this is what it looks like when we graph it. Okay. Click clear here. All right. Let me just show you where what would happen next. Okay. So we followed the gradient. Okay. So we started off at -5, 4, and using the gradient descent algorithm, it took us to -3.6, 1.75. And this is an iterative algorithm. And so what I would do next is I would start at this location, at the tip of this arrow, -3.6, 1.75. I would start here, and I would repeat the process. I would say, what is the gradient at this location, okay? And that's gonna probably be a vector that points in this direction if I want to climb up the hill in the steepest fashion. and I would take a step in the opposite direction. So here, I'm going to start at negative 3.6, comma 1.75. I'm going to calculate the gradient at that location. So if I calculate the gradient at that location, I'm going to get negative 10.075 and comma 10.55, right? And so the next iteration I will take my starting location minus gamma, which in this case I've chosen to be 0.1, minus gamma times the gradient, okay? So the gamma times the gradient is going to be a 1/10 of this, so 3.6 minus basically, or plus 1.0075, okay? So that takes me to negative 2.5925. And then over here, I've got 1.75 basically minus 1.055, okay? And if I do that, it takes me to 0.6950, okay? And so if I plot that, it will look like this. I started off here, it took me to to this location. And then if I start at this location, then the next iteration will take me to this location. And I'm going to repeat this. I'm going to calculate the gradient at the tip of this triangle, or tip of this arrow here. And we take a step in the opposite direction by subtracting off the gradient. And I will continue this. And so here I have built a small loop, okay? And this is just, I've arbitrarily just chosen 20 iterations. You know, in real life, yeah, we would probably set some kind of epsilon to say this is where we should stop. But here I've done 20 iterations just so we can kind of see how it works. And so here I say for I in 1 through 20, what we're going to do is we are going to store the current x vector into the ith row of the locations matrix. So I've created a matrix called locations, and we're going to store our x vector, which currently is negative 5, comma 4, into the ith row of the locations matrix. Okay, and then I update the x vector by using the gradient descent algorithm. I say take our current value of the x vector, subtract off gamma times the gradient at the x vector, and I've kind of split it out into x vector 1 and x vector 2, okay, and store that into basically update or replace x vector with this updated location, and then it's going to iterate and it's going to store the x vector into the second row, and then into the third row, and then into the fourth row, all the way down until it stores it into the 20th row of our locations matrix. Okay, and then I'm going to add a bunch of arrows. Okay, starting at and the arrows, the command to write arrows is you give it the starting coordinate, the x and y coordinates, or the x1, x2 coordinates in the start, and the x1, x2 coordinates at the end point. Okay, so we're going to basically start at row I and then go to row I plus 1. Okay, so you know, first iteration I start at row 1. Look at the first and second columns in row 1. That's going to be your x1, x2 coordinates, and then the end point of the arrow is going to go to the row 2. Okay, and then at the second iteration we start at row 2, and then the end points will be in row 3. Okay, so I have this going from I in 1 through 19 because our matrix has 20 rows, and so I'm only going to be able to draw 19 arrows. Okay, if I stored you know, one more, I could do 20, but so I've done 20 iterations, and this will give me 19 arrows here. Okay, and so this is what gradient descent looks like. So we've started off at -5, comma -4, and we've taken a step down here, and then from this location, the gradient descent will take me to this location, and then I do it again, and it takes me here, and I do it again, and it takes me here, and it takes me here, and we can see that because the gradient kind of gives us the magnitude of the gradient is related to how steep the curve is. is that as we get closer to the bottom and it gets a little bit more flat, okay, is that the gradients get smaller and smaller and smaller, okay? All right, is there a reason to use this over coordinate descent? Okay, yeah, so that's a good question. So in coordinate descent, what we did was we had a multidimensional function, and we would keep all other constants, all other variables constant, and we would only allow one variable to vary, okay? And we would find the minimum in one direction, and then you would update that, and then you would lock that one in, leave everything else a constant, or let the next variable vary, leave the next one a constant, and you would minimize in that direction, and so on and so forth. So gradient descent and coordinate descent, they are, I guess, different algorithms. One thing that maybe we find gradient descent preferable is that it updates all coordinates at the same time. Each iteration will update, both x1 and x2. And if you have a high dimensional function, let's say you have a function of, say, 9 variables or something, gradient descent will update all 9 in one step. Whereas coordinate descent, you basically have to run like 9 little iterations, mini iterations, just to do one full cycle. And so coordinate descent is useful, especially in the case where it's difficult to find the high dimensional gradient, which certainly can be the case. But it also has its drawbacks in that you have to basically decompose an entire function into its separate pieces. So so I would say gradient descent is probably more popular than coordinate descent, but certainly they both each have their place. Yeah. Okay, so this is what gradient descent looks like, and we can see as we get closer to the minimum, our steps get smaller and smaller and smaller and smaller. Okay, so we're first taking big steps as we're going down the hill, and then as we get closer, we're taking smaller and smaller steps. Okay. If we changed my gamma, okay, so here my gamma, my choice of gamma was 0.1, okay, and gamma is kind of the scaling factor by saying this is how big is the step, okay, so if I take the gradient and I multiply it by gamma, I'm asking, how big is the step I should take, okay? I can adjust my gamma to be something smaller, okay, so here I can have gamma be 0.03, okay? So basically my step size is going to be, 30% of what it is over here. And so my first step is a lot smaller, and then the next step is smaller and smaller. And so after 20 iterations, this is as far as I've gotten, okay? And I would get to the local minimum eventually, but it's going to take more iterations, right? And so that more iterations just means more computational time, okay? And so if you've got like a big task, like a neural network that you're trying to train, some of these things, they take hours to find a local minimum. And so you don't want to have a gamma, a scaling factor that's too small or too big. And, and what is big or what is small is going to depend, okay? So in our case, 0.1 seems to be a decent choice. 0.03 works, but would take more iterations. But you can have an entirely different function, and your gamma would need to be like 7, okay? And 7 might be the right size. So there's no magic number that says this is the gamma that's going to work in most cases. It's really hard. It's really hard to know without just doing a few test runs to see how quickly your function updates. Okay, so this is having gamma that's a little bit too small. Here's gamma 0.1. if I increase my gamma to 0.15, we can see we take much bigger steps, okay? So here I've jumped down to here, and I've jumped down to here, and it gets me to the minimum. Let me show you what happens if I take a gamma that's a little bit too big, okay? So here, I've taken gamma as 0.3, and what happened here, okay? So remember, all of these initial things, if you look at these arrows, they're all pointing in the same direction, okay? Because that's what the gradient says. The gradient points you in the direction, but it doesn't tell you how big of a step you should take. So if you look at these initial arrows, if you look at this arrow, and you look at this arrow, and you look at this arrow, and you look at this arrow, they're all pointing the exact same direction. The gamma tells you how big of a step you should take, okay? And so here with gamma 0.15, it's a fairly big step, but we took it and we end up over here. With gamma equal to 0.3, I've taken a step that's a little bit too big, okay? And what happens is, if you imagine kind of a hill and a valley, I've taken a step so big that I end up actually on the other side of the valley, okay? So rather than walking down, this slope of the valley, I've imagine the valley comes down and it curves back up. And I've taken such a big step that I end up on the other side of the valley, okay? And so now the gradient says, okay, well, if you want to go downhill, you've got to kind of go in the opposite direction, okay? Whereas over here, I'm taking big steps down, but I'm at least kind of still on the same side of the hill. Over here, my step was so big, I end up on the opposite side, okay? On the opposite side of the valley. And so now I get this weird jagged thing, like Harry Potter's scar. Yeah, I guess so. Okay. I'm not sure the reason why lightning behaves the way it does, but yeah, this is what we've got here. Okay, is choosing a gamma just trial and error? Yes. Pretty much. Okay. There have been papers and research articles covering ways to try to pick a learning rate, okay? But you can go on Google and look up how do I pick a learning rate for some machine learning algorithms or for like neural networks or whatever it might be. You can say, how do I pick a learning rate? And there's a bunch of stuff that people have written, but a lot of times it comes down to trial and error. And the recommendation is you kind of want the biggest thing that is going to work without running into a situation where you end up going back and forth and you have this weird thing. Is there a good starting point for gamma? No, I don't have one. You usually you start small, like, I don't know, 0.1, 1, 2, I don't know. And you try to push it up until it breaks, but you can start somewhere and it's still too big, or it all depends on the function. So depending on how steep the function is, which it's really hard to tell, there's not necessarily a good starting point, okay? Sorry. Okay, and so here, so that was 0.3. If I did gamma 0.5, what ends up happening is you take not only a step that ends up on the other side of the valley, but you end up actually at a steeper location on the other side of the valley. So again, remember here you got some kind of curve, some kind of, imagine a valley, and the idea is you want to get to the bottom of the valley. But in this case, when you're on one side of the hill, it says to get towards the bottom, travel in that direction. But what happens is you've taken a step so big that you end up on the other side of the valley. And not only that, but you end up at a steeper location on the other side of the valley. And so when it says, so we've taken such a step that we end up like probably way over here. And when you calculate the gradient at this location, it says, no, go back in the other way. And you went too far. So you got to go back the other way. And you overcompensate and you end up really far on the other side, and it just ends up being crazy. So let me just show you more examples. But But before we do that, let me just go into matrix notation, because this is going to be more efficient and better than having to find all the partial derivatives. So remember back here, what we did was we took the gradient and we declared them as partial derivatives. Okay, we calculated them as partial derivatives, and it's working. But let me just show you what it looks like when we do it in matrix notation. So in matrix notation, our loss function looks like this: t minus xw transpose t minus xw. Okay, and our loss function is a function of w, right? Okay, so this was non-matrix notation. So in matrix notation, we're going to find the gradient of L with respect to W, okay? And we did this a lecture or two ago, okay? And so this is the gradient with respect to W. And what we did in that lecture is we said, okay, well, here's the gradient. We're going to set it equal to 0 and solve for W. But in this case, we're not going to set it equal to 0 and solve for W. We're going to say, okay, this is the gradient, and now I'm going to use this for gradient descent, okay? So that's the difference. So you still have to find the gradient. You have to find the gradient. But rather than setting the gradient equal to 0 and solving, you're going to just take the value of the gradient and use it iteratively to go down the hill. All right, so here's my gradient. dl dw is x transpose t plus x transpose xw. And in matrix notation, the gradient descent looks like this. We're going to take our current location of w at time n and subtract off gamma times the gradient of f, okay? And so this is my gradient, okay? Here I've just multiplied it by a constant n over 2 to kind of get this. So I've got negative x transpose t times x transpose xw. So I've gotten rid of the constant here, and I've coded that up here. So I've got negative x transpose t plus x transpose xw. So this is the gradient, okay? So I've created a function that's going to calculate the gradient. Is that all right? And then, and in this case, the gamma I have to use is 0.02, okay? The gamma I'm going to use is 0.02. And I'm going to start off using a w vector with the values -1, 1.5. And I want to find the minimum, the minimum of this function, okay? And so this is the thing that I'm working on here is for ordinary least squares, where my function is, my loss function is this, okay? And the gradient of the loss function is calculated as this, okay? And so here I've done the gradient descent algorithm, and I start off at my w vector of -1, 1.5, and I'm going to run 1,000 iterations of this, where basically I'm going to just calculate the gradient of this w vector at this w vector, do gamma times that, and I'm going to update my w vector by doing this. Okay, and after 1,000 iterations, it tells me my solution is 1.799995, 3.1001. Okay, and basically what I'm trying to do is I'm trying to find the slope and intercept of the line that fits these 3 data points. Okay, I've got 3 data points in a line, and I'm trying to find the slope and intercept. The true slope and intercept is 1.83.1. Okay, and I just started off at some arbitrary location, -1, 1.5. I run 1,000 iterations of gradient descent, and after 1,000 iterations, it gets me close to the true solution of 1.83.1, and tells me I'm at 1.799995 and 3.10001. Okay, which is pretty close. Let me just show you what this looks like. Okay. This is just code to get the graphs on the thing, okay? This is the plot of gradient descent. This is what the loss function looks like, okay? 3D contour of the loss function looks like. And gradient descent looks like this, okay? I started off at this location, -1, 1.5, which is this location here, and gradient descent takes me down here, going down the hill, until I reach here, and then it takes a sharp turn, and it gets me towards the center. The center is going to be located at 1.8, 3.1, okay? So remember, these coordinates represent the slope and the intercept. So I start off with a slope of -1, or is it I think, okay, I'm sorry, this is the intercept. I start off with an intercept of -1 and a slope of 1.5, okay? So this is what it looks like, all right? So here are the 3 points. Here are the 3 points and I'm trying to find the slope and intercept of these 3 points. Okay, slope and intercept that's going to best fit these 3 points. And I'm starting off with an intercept of -1 and a slope of 1.5. This is what my fitted line looks like right now. Okay, so my fitted line looks like this, and we can see this does a terrible job of fitting these 3 points. Okay, so with gradient descent, I start off here, and it says, yeah, you've got very big squared error. Okay, and so at the next iteration of gradient descent, it says, okay, if you take a step, what you should do is you should increase the slope, okay, from 1.5 to 2.3, okay? So increase the slope, and that's going to reduce your loss, okay? So we've increased the slope, and it's reduced our loss. We've also adjusted my intercept to -0.77, and this is what I've got so far. Okay, this is still not great. And it says, okay, if we do gradient descent, let's try again. Let's keep heading in this direction. The next thing, it says increase the slope some more. Okay, so after a couple iterations, I've increased the slope, and now I've increased the slope to 3.33, and I've changed my intercept to -0.459. Okay, and again, we can see just between these lines, my starting point and this one, we can say this one does a much better job of fitting the 3 points. Okay, it's not great. Okay, we can see this is not a good line. It's all on one side, and we're going to have a fairly significant loss. But we can see that you know, what we're doing is we're adjusting the slope and the intercept, and we can see this does a better job of fitting it. Okay, and so here now it says use a slope of 3.63. Okay, and have an intercept of -0.236. Okay, so at this point our slope is probably a little bit too high, and what I need to do is I probably need to kind of just adjust that line just a tiny bit, right? So I started off with a slope that was too shallow, and I've brought it up, and now I'm trying to kind of fine tune it. Okay, so this is, I started off here, and what I'm doing is I'm increasing my slope, getting it a little bit higher, and I'm going to just kind of iterate. And so there's a whole bunch of iterations here, okay, that I'm going to kind of skip through. And so after a bunch more iterations, it's kind of adjusted my slope. My slope is now 3.184 with an intercept of 1.475, and that gets us pretty close. Okay. And so, so this is what gradient descent is doing. It starts off at some location, and you just keep updating, updating your slope and intercept, or whatever your W terms are, by moving in this direction here. Okay. Again, here is just, if you change your gamma a little bit, I've got gamma equal to 0.05. You can see we end up taking a step that's too big, and we end up on the other side of the valley, and we go up and down, right? And so here, the gamma 0.05 is too big, okay? And again, it all depends on the situation that you're in, what size gamma to use. So here, gamma 0.05 is too big, but it still gets us to kind of the minimum, okay? Here at gamma 0.07, it just goes, it goes crazy. Okay, so this one's no good. Okay, and these are just some issues that can happen when you choose a gamma that's too big and things like that. Oh, I'm going to run out of time. Okay, so the last couple of slides, let me just show you how you can estimate the gradient numerically. And this is going to be an important thing to kind of just verify your work, right? So sometimes it's hard to find the gradient via calculus, and sometimes you find the gradient, but you're just not confident in your skills, and you're not quite sure if you did it correctly, right? So this next method is one way for you to check to see if your gradient kind of aligns and makes sense, okay? This is what we call the numeric gradient. It's simple, but it's very inefficient, so you wouldn't want to do this. You'd want to find the analytic gradient in order to do the calculations, but in order to just kind of verify your work, the numeric gradient is useful, okay? And so basically what you're going to do is just like taking the numeric derivative approximation, is you're going to just add on a tiny constant, okay? You're going to add on a tiny constant like 10 to the negative 5 or something like that, and you're going to see how much has the function changed, okay? And as far as the numeric gradient goes, is you're going to add on a tiny constant, but you have to do it for each component, okay? So in our case, if we have two, if W is a vector dimension 2, you have to add your H, 10 to the negative 5 to the first component by itself, leaving everything else a constant. And then you do it to the next component, you add H to the next component, leaving everything else a constant. So you would do something like that. And so, so your gradient is still going to be in 2 dimensions here. And so, so this is kind of our earlier function that we did. And we started off at negative 5 comma 4. And so we're going to evaluate the function at negative 5 comma 4. It evaluates to 85. Okay, the function, if you plug in all of the values, negative 5 comma 4, it evaluates to 85. And then this is what we do. We have to do it twice. We have to do separate things. I'm going to add on 0.01 to negative 5. Okay, normally we would add something around 10 to the negative 5, but just for illustration, I'm going to add 0.01. Okay, so I get negative 5 plus 0.01. So I get negative 4.99 comma 4, and we're going to calculate what this function evaluates to versus 85. So when I evaluate this function, I get 84.8601 versus 85, and then I subtract it by, or divide by how much I added, in this case 0.01. And when I do this calculation, I get negative 13.99. Right? Over here, I do the same thing. This time I leave negative 5 a constant. Okay, I don't touch negative 5, but I change 4. And so I compare what happens to 4.01 versus 4. And we know this function evaluates to 85. When you evaluate this function, it comes out to 85.22525. And so how much did this change with respect to our adjustment in X2? It changed by a factor of 22.525. And so, so our numeric gradient estimate is negative 13.99 comma 22.525, right? And that's very close to what we got analytically back on slide 10 of negative 14 comma 22.5. So, so this is one way for you to verify that what you did analytically makes sense by doing a numeric gradient check. And this is going to be recommended anytime your gradients are complicated. All right, let me give you the second quiz answer. The second quiz answer for Wednesday is C as in cat. Second quiz answer for Wednesday is C as in cat. All right, so with that, we will end. We'll end the lecture for today, and we'll see you guys on Friday. Okay, and all right. So Have a good day. Stay safe out there, and we'll see you guys on Friday. So let me stop my recording for today.